Thank you for coming to this talk. I'm Seunghoan Song from Nagoya University, and this is a joint work with Masahito Hayashi. The title of this talk is Capacity of Quantum Private Information Retrieval with Colluding Servers. So in this talk, I consider private information retrieval, which I call PIR in short. So what is a PIR? The PIR protocol can be understood by comparing with the retrieval protocol without secrecy. So in usual case, let's say that a server contains F files M1 to MF, and a user wants to retrieve the case file MK. In that case, the user sends K and downloads MK so that the user knows MK. However, in this case, the server also knows the user's information K, which one is requested. So in PIR, we want to keep this K secret to the server. So for that purpose, the user sends Q, some query instead of this K, and gets some answer to retrieve the MK. However, the server shouldn't know at the end of the protocol, so this server's information Q should be independent of K. So we write it by the mutual information between the K and Q equals to 0. It seems that it's very hard to find the solution of this problem, but there's a very simple solution of just downloading all messages. So by just downloading all messages, the user can pick the targeted one, MK, but the server doesn't know which one is the targeted one. So this is a very simple solution, but very inefficient solution because downloading all messages is very inefficient. The efficiency of this protocol is evaluated by a PIR rate, which is the size of MK over total download size. So from definition, it is less than 1. And the PIR rate of this trivial solution is 1 over F because there are F files and the user retrieves only one file. However, unfortunately, it is proved that this trivial solution of downloading all is optimal. So people have started to consider multi-server PIR problem. In this case, there are multiple servers. This figure is only for 2 servers. Each server contains the same copy of the classical files, and they are assumed to assume that they do not communicate with each other. So in that case, the user secrecy is defined for each of the servers. So each server shouldn't obtain any information of this K. So, and the PIR capacity have been studied for only 4 years ago. And the capacity is defined as a supremum of this rate. And they derived that this value is the capacity. So this value depends on, in here, the N is the number of servers and F is number of files. And this value depends on both of these N and F. And last year, in our previous work, we extended this result to the QPIR case, quantum PIR case. So in this figure, the green ones are classical information and magenta is quantum information. So we consider the case that each server contains the classical information and query is classical and the download is quantum. However, we also assume that the servers share some prior entanglement before the protocol starts. And furthermore, we also considered some other secrecy called server secrecy, which means that the user only obtains the MK. So we considered both of these secrecies, and with these secrecies, we derived the capacity is equal to 1. So this value doesn't depend on the number of servers N and number of files F. And in this talk, we consider the T private QPIR. T private QPIR is a little bit extended class of this problem. The protocol is exactly the same as the previous one, But the only difference is that some servers may communicate to know this K. So and most T server most T servers are allowed to collude, it is called the T private to PIR. And we derive the capacity of this problem, which has two cases. So when less than half of servers are colluding, then the capacity is equal to one. So this result is the same as this one. So it's very good result of the capacity one. This still applies for the case of some colluding, the small colluding case. But if the number of colluding servers are greater than half of the servers, then it decreases a little bit. So here is the table of our results and the classical capacities. So the red one is our result. So we derived that T private to PIR capacity and T private symmetric PIR capacity. Here the symmetric means that we also consider this server secrecy, and we derive that our capacity result is greater than this classical result. So in the remainder of this talk, I will explain how we can prove this one. So first, we will construct the T private QPR protocol, the optimal protocol. But we only prove construct the protocol for when the T is greater than n/2, because for the other case, our protocol for T equals n/2 or achieve the capacity one. So we only consider this case. So let's start the protocol construction. So in our protocol, we use the stabilizer formalism. In stabilizer formalism, this n-tensor system of q-dimensional Hilbert space is related to 2n-dimensional vector space over finite field FQ. And a stabilizer is defined from self or orthogonal subspace V. And when this stabilizer is determined, a Cauchy space, some quantum system Cauchy space is determined. This Cauchy space is a space stabilized by this W operation for all vectors in this V. So with this stabilizer formalism, we can consider this line of information processing task. So let's say that a story state row is prepared on this Cauchy space, and some operation, quantum of W operation, is applied. Then by applying some measurement, which is also usually called the syndrome measurement, we obtain some classical information as plus V perp. So stabilizer formalism is often used for the error correction. So in the error correction case, the error correction operation is applied depending on this measurement outcome. So we use this line of, but we don't consider any error correction. So we use this line of process in our protocol construction. So in our protocol, we prepare the prior entanglement between the servers as a state on this Cauchy space, and by controlling the queries and depending on this file information, the server's operation will be this WS. And then by applying some decoding measurement by the user obtains this as plus V, the classical information, as a retrieval outcome. However, this line of process, is just a copy of this process, but this process is not QPIR at all. It is. So for making this protocol as a QPIR protocol, we need to make this retrieval outcome is the same as this targeted information MK. And during this process, we didn't consider any secrecy conditions. So you need to satisfy the user secrecy and the server's user secrecy and the server secrecy during this process. So we construct some sophisticated way to make these two conditions are satisfied. And but the essential point is that satisfying these two conditions reduces to the problem of finding the V, the stabilizer V, which has good property. So what is a good property? So for finding this V, we use this lemma 5.2, which says the existence of some matrix D1 over finite field FQ, whose column vectors V satisfy some self-orthogonality condition. So it defines the stabilizer V, and the row vectors of this matrix satisfy some linear independence condition for any pattern of the permutation in pi. So using the V defined from this lemma, we construct our QPR protocol. For explaining the intuition of how we can construct, I want to explain the classical one. So the classical version of this lemma is written like this: that any t rows of some matrix are independent. And in many classical cryptographic protocols, such as PIR and secret sharing, this property has been used. And in that case, some kind of n-t information is transmitted by this method. So in our protocol, we use the similar approach, and we achieve this 2 n-t information. We make this 2 n-t is transmitted. Because we have these two, because we use the bit information and phase information in this bit information and phase information for transmitting the classical information. So this is the idea how we construct our QPIR protocol. So next one is the converse bound. So we have two converse bounds depending on this range of t. So the first one is C is less than 1. So for doing that, we just reduce our protocol to 6-channel coding. How do we do that? We just group all of these servers as one agent. And then the downloading process of this protocol is considered as sending quantum systems for sending the classical information MK. And from the result of the secret channel coding, we know that the size of MK is less than the dimension of this transmitted quantum system. And from this result, from this inequality, we can derive that the C is less than 1. So next one is for this bound. And first, we also use the similar approach as the previous one. But in this case, we use the 6-channel coding with entanglement. So we will reduce our protocol to this problem. And for doing that, we just give the user the power to distinguish which servers are colluding. But in our model, the user cannot distinguish which ones are colluding. But we give power to this protocol. And then in our paper, we prove that the information from colluding servers can be considered as a shared entanglement. So then we can apply the result of the secret channel coding with entanglement. So then the classical message size is less than the twice of the dimension of the transmitted systems. And because there are n-t non-colluding servers, these 2 n-t comes out from this equation. So using this result, the capacity is upper bounded by this value. So this is the end of our converse proof. So as a conclusion, we proved the T private QPR capacity is this value, and we also constructed an optimal protocol in this case. So this is our result, and it is greater than the classical results. And there are several open questions. One is the trade-off between the QPR capacity and the amount of entanglement. In our case, we didn't restrict any entanglement amount. And there are many quantum extensions for many classical results. And we can also consider some application of our protocol to other problems. Thank you very much.